In this video, we want to talk about planes and the equation of a plane and how we can define a plane from the vectors in the plane and a vector that's normal to the plane. So let's just talk about for a second here. We have the image of a plane. So if I have three-dimensional space and we say that this is the x-axis, y-axis, and z-axis, we have a plane which is just a flat surface in three-dimensional space. You can think about it as a piece of paper that's just suspended here in three-dimensional space. And you want to think about a plane as just a collection of vectors. First of all, planes go on in every direction infinitely. So the plane will go on in all of these directions infinitely, but obviously we can't show the infinite plane, so we just draw a section of it. And a plane is just a collection of vectors that all lie in the plane. So if I sketch a bunch of vectors that maybe are in this plane, they might look like this. And you could just think about all of the vectors as just lying on the surface of this flat sheet of paper. So if I had a flat sheet of paper and I drew a bunch of vectors on it, that would be like vectors defined in the plane. And then you'll have a normal vector. And the normal vector will be a vector that is perpendicular or orthogonal to the plane. And so the normal vector always forms a 90-degree angle with the plane. If we think about something like this, where we have the flat surface of the plane like this, and then the normal vector, and then we have a 90-degree angle here. So this normal vector is sitting at 90 degrees to the plane. It's orthogonal to the plane. And we can go ahead and call that normal vector the vector n. In order to define the plane, we're looking for a vector that's in the plane. So let's say we take this one that has its initial point right here and its terminal point right here. And let's say that we take two vectors that come from the origin to the initial point and the terminal point of this vector. So we have this first vector here and this second vector here. We could call one of the vectors x naught. We write this when we have a 0 here, we write this as x naught. And let's say the point that it points to, the initial point of the vector, is just the point x naught, y naught, z naught. And then let's say that this second vector here we'll just call regular x, and that points to a point x, y, z, which is the terminal point of this blue vector. In other words, if we just define these 2 points as either end of the vector, then we can get the blue vector by subtracting one of these from the other one. So we can say that the blue vector is really, we'll say, x minus x naught is equal to, and then remember that we would just subtract one component from the other. So we get here x minus x naught, y minus y naught, and z minus z naught. And these are then the components that define this blue vector, and we know that blue vector lies in the plane. The reason that vector in the plane is helpful, because if we know this gives us a vector in the plane, that vector is perpendicular or orthogonal to the normal vector. The normal vector is orthogonal to every vector that lies in the plane. So we can really say that the dot product of the normal vector and this vector we found that lies in the plane, x minus x naught, is going to be equal to 0, because remember, when we take the dot product of two orthogonal vectors, that dot product is always going to be equal to 0. So if we then define the normal vector, we'll just call it the vector a, b, c, then we can really take this dot product and we say that the normal vector is the vector a, b, c, and the vector that lies in the plane is this vector we found here, which is x minus x naught, y minus y naught, and z minus z naught. And that's equal to 0. And so then when we take the dot product, what we get is a times the first entry plus b times the second entry plus c times the third entry. So we get a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. And this equation here is the equation of a plane. This is the standard form for the equation of a plane. So we can use this to find the equation of the plane instead of having to derive it from the normal vector and a vector in the plane. So if we use an example then, let's say that we have a normal vector, and that normal vector n, we'll call it here, we'll say this is the normal vector n. We'll say that n is going to be equal to, let's say, 2, 5, -3. And we'll say that we have a point in the plane, the point x0, y0, z0. And let's say that point is 1, 0, -2. Then we can plug the normal vector and the point into the equation of the plane to find the equation. So here's what that looks like. We say that we match these up. We say that this is A, B, C, and this is x0, y0, z0. So we just plug in, and we get 2 times x minus 1 plus 5 times y minus 0 minus 3 times z minus a -2 or z plus 2 is equal to 0. And we could leave the equation of the plane this way, but we would probably at least want to simplify this y minus 0 to just y. And if we multiply everything out, we can simplify in a different way and get 2x minus 2 plus 5y minus 3z minus 6 is equal to 0, or 2x plus 5y minus 3z, and then we usually collect all of our constants on the right-hand side. So over here we have a -2, and then minus 6 is a -8. So we have a -8 on the left side. If we add 8 to both sides, we get a +8 on the right. So this then is the equation of a plane. So what we can say is that if we start with the standard form of the equation of a plane, and then we plug in the normal vector and a point in the plane, we're always going to be able to simplify down to a form that looks like this, and we can match that up with ax plus by plus cz is equal to d. And the reason that we're interested in this format is because in this format, the normal vector, you can see, is actually always going to be a, b, c. Remember that we said the normal vector was 2, 5, -3, and notice that we still have down here 2, 5, -3. So when we have the equation of the plane in this format, all we need to do to find the normal vector is look at our coefficients here, and we always have to remember to include a negative sign if we have one in front of any of these values. So we can say then that the normal vector from this plane, we can pull it directly from the equation and say that it's 2, 5, -3. The thing we want to realize here is that the value of the normal vector doesn't change regardless of the value on the right-hand side of the equation. And if you're wondering why that's true, it's because no matter what value we have on the right side of the equation, that's just shifting this plane up and down. In other words, we're just shifting the plane down or shifting the plane up depending on the value we have here on the right-hand side. So if we have 8, it might be at 8. If we change it to 6, it might shift it down 2 units. If we change it to 10, it would maybe shift it up. But we're just shifting the plane. We're not changing the orientation of it. So regardless of how we shift it one way or the other, the normal vector is still the same. The normal vector is still the vector that sits orthogonal to that plane. So we could change this 8 to 10. We could change it to the square root of 2. We could change it to the exponential value e. We could change it to a 0. It doesn't matter which constant we change it to. The normal vector is still always going to be 2, 5, -3.